Hello everyone, welcome to this poster presentation entitled Fabrication of Nickel Oxide and Zinc Oxide PN Junctions via Reactive Pulse Laser Deposition at Room Temperature for this 32 International Material Research Congress. My name is Yvonne Silva and currently I am a PhD student in CISESE. My thesis advisors are Oscar Contreras and Wenzel de la Cruz, researchers in Nanoscience and Nanotechnology Center of UNAM. Well, to start, I will give a short introduction to the topic. Nowadays, semiconductors PN junctions are used mainly to fabricate electric current. However, they are also used in bipolar transistors, field effect transistors, LEDs, solar cells, and recently gas sensors. Specific properties are required in some applications, such as being transparent, having a wide band gap, having the high capacitance, or being capable to interact with other chemical species. As a material, many of these metal oxide semiconductors can meet these demands if they are properly synthesized. Some of these applications require uniform deposition of the semiconductors as thin films. Physical techniques like pulse laser deposition allow the deposition at room temperature, decreasing the time of fabrication. In this work, we pursued to fabricate a microdiode with two metal oxide semiconductors using reactive pulse laser deposition as deposition method and photolithography for delimit the sizes. Clean glass substrates were used to fabricate the devices. Nickel oxide and zinc oxide ultra-thin films were ground at room temperature under 25 and 5 milliliter oxygen pressure, respectively, using nickel and zinc metallic targets. To ensure that the thin films were metal oxide, chemical composition measurements were taken throughout X-ray photoelectron spectroscopy. Also, to know their physical structure, X-ray diffraction measurements were acquired. Additionally, the electrical properties of semiconductor were characterized using Van der Pau and Hall effect technique. To determine their optical band gap, the TAUC method was used for the calculations from UV-Vis spectroscopy measurements. Now, regarding to the results, first, their electrical properties showed that nickel oxide is a p-type semiconductor since their electrical carriers are holes. Instead, zinc oxide is an n-type semiconductor with a lower resistivity than nickel oxide. In both materials, the mobility is the same order of magnitude. All these electrical characteristics correspond to the properties of semiconductors. In turn, the X-ray diffraction results show that both thin films are polycrystalline. It is interesting to see that two peaks correspond to crystalline planes of metallic zinc. However, if we see that XPS survey spectra, they show the presence of zinc and oxygen for zinc oxide and nickel and oxygen for nickel oxide. For the position of nickel 2p and zinc 2p peaks and the intensity of the oxygen 1s, we can realize that both thin films are oxidized metals. Since XPS is a technique for the chemical characterization of the surface, it is not a surprise that we can see metallic zinc as we see in XRD results. Those small crystallites are probably in the bulk. Additionally, from the high-resolution windows, we have estimated the stoichiometry of the samples. From the transmittance of both semiconductors, the zinc oxide is the most transparent. Using these measurements, we obtain the tau plots where we have made a linear fitting. The intersection reveals a band gap of 3.2 electron volts for zinc oxide and 3.25 electron volts for nickel oxide. Finally, the results of the electrical evaluation of the device indicate a bulk-in voltage of 0.6 electron volts. This result is comparable to devices made from crystalline silicon. To be sure that these results are a product of the p-n junction, we verified that the contacts of the semiconductors with their respective electrodes were ohmic. As shown in both plots, we can conclude that the change in the current is indeed a product of the p-n junction. Finally, the big conclusions of this work are from the XPS spectra, we see that both are metal oxide films. Both semiconductors are polycrystalline despite being grown at room temperature and turn out to be transparent with broad band gaps. A device was successfully manufactured using this methodology, and the p-n junctions is promising for other specific applications such as selective gas sensors or LEDs. We want to acknowledge for all the technical assistance throughout this work, and thank you for your attention.